Okay, so let's get started. Our next talk is going to teach us how to visualize, analyze, and correlate network activities for parallel programs on InfiniBand HPC clusters using the OSU INAM tool. And this is going to be a joint talk by Dr. Hari Subramoni and Pouya Kousha. So starting with Dr. Hari Subramoni, for those who are not here, he's an assistant professor in the Department of Computer Science and Engineering at the Ohio State University since September 2015. His current research interests include high-performance interconnects and protocols, parallel computer architectures, network-based computing, exascale computing, and the list continues. He has published over 100 papers in international journals and conferences related to these research areas. He has been actively involved in various professional activities in academic journals and conferences.
If I were an assistant professor from 2015, I would have been fired by now.
And he's doing research on the design and development of MUG'22 and high performance, that's including high performance MPI over InfiniBand, iWarp, and Rocky, and so on. And the second speaker is Pouya Kousha, who is currently a PhD student at the Ohio State University, supervised by Professor D.K. Panda. His research interests are parallel algorithms and distributed systems, high-performance computing and profiling tools. His work primarily focused on scalable and real-time analysis, monitoring and profiling tools, and how to use them to solve the bottlenecks and optimize MPI libraries and applications. So without further ado, let's welcome our speakers today.
Thank you for the kind introduction. There'll be three of us. So Ayappa Poli, he's a master's student, so he's sitting back there. So again, as I said, I come and talk. The actual work is done by all of our heroes who put in like all the days and nights of work. So this project has been running for like the last like 5 or 6 years in our group. The goal is trying to see how we can visualize, analyze, and correlate different activities. Okay, so I think Moshe was presenting a little bit about how can you quickly recover from, let's say, congestion kind of events. Now, how do you figure out that these kind of events occurred? So how can you create a system which can figure out that, like, let's say, how do you relate the cause and the effect? So that is what we are trying to do here with the OSU INAM tool. So this is kind of an overview. This will be more like a demo. So we give this tutorial at like various events. This is typically done as a hands-on where we allow people to kind of let's say play around with the system. But because of lack of time, we are not able to create that. If you are interested in, let's say, playing around with the system, we can create like a sandbox environment for you like later today, so that you can do that. Okay. So let us know if you are interested in that. So if you look at it, with the recent advances in HPC, you have a new set of challenges. So the problem is basically, how can we identify performance issues? How can we relate the cause and the effect? So one of the most common issues that we hear is that, hey, my application ran fine a week ago, no issues, but when I ran it yesterday, I don't know what happened. It took like 3 times the amount of time. So what happened? So if you are an administrator of an HPC system, I'm sure that you would have had this question at least a few times in your career, if you're lucky, if not more than that. I see some people nodding their head, so I think I hit the right chord there. So how do you actually figure this out? If you look at profiling systems, you have a lot of profilers. You have profilers for applications, you have profilers for MPI libraries, you have profilers for the network, and you have profilers or, let's say, tools to do accounting of the job scheduler. But there is nothing really that puts them all together and tries to correlate the information you get from one system and another system and, let's say, try to link the cause and the effect. So that is, in a sense, what we are trying to do here. So we are trying to see if we can have a unified and holistic view for all users as to what actually happened. Okay. So this is kind of a comparison of what INAM does with a lot of other tools. So again, all these slides will be available to you. I will not go over like the huge laundry list, but broadly, what we are INAM is allowing you to do is trying to compare your application, your network fabric, and your job scheduler and your MPI runtime in a holistic way. So we are trying to cross correlation of information. So through this cross correlation, we are hoping that we will be able to understand the interaction between all of these components, the application, the MPI runtime, the communication fabric, the IO subsystem, in a holistic way. And that's the challenge that we are trying to address. So this is being done as part of the MBAPICH project, as you all know. And recently, we made a release of OSU INAM with support for newer database options. So continually, we are working to see how we can add more features, more scalability, more performance. So far, OSU INAM was working using the MySQL or MySQL, whichever way you want to call it, database. But we saw that when you go on like very large systems with thousands of nodes, like 2,000, 4,000, 8,000 nodes, the MySQL database is, let's say, a significant bottleneck for insertion and querying. So we tried to explore a lot of other options, like we explored the Apache Spark, we explored other time series database like InfluxDB, and finally we settled on the InfluxDB option to improve the overall insertion performance. So that is available with the release that we did earlier this year. So we use the InfluxDB database option, and that significantly improved the performance, a lot of operations inside OSU INAM. So OSU INAM has various components, which each component interacts with a different subsystem. So it has like a web server, which provides a web-based user interface. So the advantage of a web-based user interface is that you can, let's say, suppose you are in a meeting somewhere around the road, you can pick up your phone, open a web browser, connect securely to your INAM server running maybe halfway across the world, and try to figure out what exactly is happening. So that is why we chose the web-based approach. On the back end, we'll have a server with the daemon running, which collects data from a lot of different entities on your HPC system and stores it on a high-performance storage, which can either be currently MySQL or InfluxDB. And these are the kind of metrics that we query from the fabric, the job scheduler, as well as the MPI runtime. So all of these are queried in real time and remotely. So that is one important thing. So if you look at other tools, for instance, if you look at the tool from Sandia, I forget its name, but
LDMS.
LDMS from Sandia, it needs to have a daemon on each compute node. So that daemon would need a compute core associated with it, and that will take that core away from the application. So that is not from what we have seen like the best approach. So here what we do is we try to query all of these things remotely from the server by interacting with the OpenSM, the subnet manager, the switches, the network adapters, and stores it on the cluster in real time. Okay, so and once we have done this, we are able to also visualize these changes that happen in real time, and this is the overall flow in which we expect things to work out. So we expect that the user would be using like a web-based interface on like a cluster with high performance or deep learning applications, which would be monitored by OSU INAM, which would collect the metric, give some insights and recommendations, and the user would get that, and he or she would run the application again with newer tuning. Okay. The most important question, yes, Moshe.
So what type of MPI support that?
Sorry?
What type of MPIs support this MPIT extension?
So currently MBAPICH2 supports it. So again, this is not standardized. So we use the MPIT PVARs, and the MPIT PVARs has an event-based ecosystem. So we use that event-based sampling to get the data from the MPI runtime and give it to OSU INAM. But the problem there is that the names of the PVARs, they are not standardized across MPI libraries. So the names that maybe Intel MPI uses could be different from what OpenMPI uses and could be different from what MBAPICH2 uses. Since there is no standardization there is a bit of a hurdle. So currently only the MBAPICH2X communication runtime has this integration with OSU INAM. So this is something that I have brought up in the MPI forum in the past. So again, having an agreement between multiple different partners in the community takes time. So it is in the works. So once that kind of standardization is there for the PWARs as well, this would naturally become applicable to like multiple
Because
MPI libraries.
OpenMPI, for example, have this PMPI.
So they are two separate things. So you have PMPI and you have QMPI, which is the next version of PMPI. So that is the profiling interface for MPI. That is an interception-based method. So when you call MPI send, you would go to PMPI send, then it will come back to MPIR send.
Machine.
Sorry?
Then you need it on each machine.
Yes. So once you do the interception, you have a performance impact. Okay, so that is what I'll be talking about next, the kind of overhead that you have.
So one more question on that. So how is the machine learning framework does it?
How is the what?
The machine learning, like the PyTorch and TensorFlow.
So if you look at all of these machine learning frameworks, they have different communication substrates. Now, Horoward is a very popular communication substrate for TensorFlow, PyTorch, and MXNet. Now, Horoward underneath has the ability to use MPI or Nickel or other communication substrates. So typically what we have seen done is Horoward would use MPI, and if that MPI is MWAPIsh2, then we are able to get that information from MWAPIsh2 directly into OSU INAM. So that's how that flow would work. Now, PyTorch recently has this PyTorch distributed interface, which directly goes over MPI instead of going through Horoward. So broadly, what we see is that even on the deep learning side, people are beginning to learn more about MPI and beginning to adapt to it, because that gives a lot of portability. Because MPI is there on almost every single supercomputing system, and nowadays you really can't run deep learning without a supercomputing system, right? So we are seeing that trend where almost everything is kind of trying to use MPI as a common runtime. And actually, Dr. Amir Shafi here is working on like a solution where we are trying to move Apache Spark over MPI as well. So can MPI become that common communication runtime for big data, deep learning, machine learning, all sorts of solutions? So Dr. Amir Shafi from our group is leading that effort, trying to see if ML, DL, big data, all of these, let's say, higher level programming models can use the MPI runtime. So we have a paper accepted at Cluster, which will be presented in a couple of weeks, where we are trying to see if we can move like Spark over MPI. So Kinan sitting here, so he is the first author in that paper, and Dr. Amir Shafi is leading that effort from our group. So I hope that answers the question. So again, as I was talking about LDMS, the problem is overhead, right? So we want to see how much like overhead there is, and if we can, let's say, minimize that and have little or no perturbance on the entire system, because OSU INAM is running. So here we look at the overall overhead for fabric discovery. So we and this only needs to be done once or maybe twice, or whenever there's a change in fabric. So we don't expect this to happen like that very frequently. So through the work that we did, we are able to reduce the overall time for like fabric discovery, like from, let's say, hundreds of seconds to like maybe like a few seconds. So this is like significant impact. And this kind of shows the more of the things that happen on a like let's say live basis. So like port inquiry, so where you are querying the port. So here the time taken is even lower. It is like sub-second latencies. So that is what we are seeing here. So we had enhanced the OSU INAM to ensure that we are able to query all of these hundreds of ports or switches with sub-second or extremely fast. Okay. And this is the looking at the overhead of collecting data from the MPI runtime as well as visualizing it. So all of these, as you can see, is in the milliseconds or nanoseconds range. So overall, there isn't a lot of overhead for like the data collection, the data processing, as well as the visualization phases for different systems. So this is again like the application level analysis, trying to show at an application level. So let's say if a real application is running, for instance, like an AS benchmark, and the underlying MPI runtime is actually collecting data and exporting it to OSU INAM. How much impact does it actually have on the execution time of the application? And as you can see, the overhead is like very, very, very low, less than 1% overhead. So we feel that that's a reasonable overhead. reasonably like acceptable overhead for the kind of benefits that OSU INAM can give. Now, having said that, we'd like to give like detailed overview as to how you would download and install and configure OSU INAM, and also like a bunch of demos. So for that, I'll hand over to Pouya. So before that, any questions on the high-level goals or things like that? Okay, if not, Pouya.
All right, thank you. OSU INAM is available through our website. We have it for different MOFIT versions and different packages for ARM and also x86-64. We also have done modeling of the amount of traffic we put on the network, and also amount of modeling of traffic that you store. Both of these are available in details in our papers listed on OSU INAM webpage. But basically, considering OSC cluster that is around like 1,500 nodes, the port inquiry that is for InfiniBand network query, that the data would be generated would be 1,600 kilobytes per second. The fabric discovery will be 800 kilobytes per second. And given that the OSC cluster, the links are capable of 56 gigabit per second to 100 gigabit per second, this traffic injected into the network is insignificant. So that's why we are able to give very low overhead. Same thing here for the MPIT. Due to lack of time, I just skipped this part. So we have a user guide that has all the information on how to install the OSU INAM, how to configure it based on your cluster size. We support both InfluxDB and MySQL. So the steps that you need to take are all explained over there step by step. So for example, as I mentioned, depending on the cluster size, we tell you like how you should allocate the resources on the node that you're running OSU INAM between different components of OSU INAM daemon to get the best performance. And through our papers, we have shown how by following these instructions, different colors represent different threads that we are having on each component. The load is balancing between them equal. So it comes to the point that how do you configure INAM to get information from MPI job? And we wanted this to be the minimum. So all you need to do is to pass a file that's inam.conf to the mVapage job that contains these parameters. The QPN LID, which gives the address of the INAM node that is gathering the data, and then a set of like intervals and like reporting different metrics that you can enable or disable them. So you can also set a counter interval, for example, from 30 seconds to 60 seconds or whatever you like. So it's something that a user can decide on the interval for profiling. So then it becomes a question like, what should be the profiling interval that I want to gather the data? And we have two choices here. Like it's a trade-off between low intervals of like 1 to 5 seconds. You get a very fine grain profiling, but the problem is like you're going to have a lot of data. And it would cause some delay in the web interface. For example, let's say if you want to gather everything for the last 5 hours, then it takes some time to gather all of those, render those, and show it. On the other side, if you go for larger data, for larger profiling data, then you might lose some granularity, but you will have faster web interface. Just a note that we have a database size calculator on our web page that you can see and play around to see how much profiling granularity will produce how much data. As I said on the MUG'22 job, only the green ones are the ones you need to add the runtime parameter to your script. And one of them is the INAM config file, and the other two are used to just provide the necessary things for INAM to collect. There is also another mode that we show some p-values. The p-values are a little bit more, but they're all mentioned here. So with this, I'm going to go over a demo of OSU INAM. Note that this is not all the features. I'm going to just show the most important ones. So on demo number 1, I want to see how can I visualize my entire network. How many of you have seen your the network of the cluster that you're using? Just one. Okay, so this is two. Yeah. Okay, of course. So a lot of people they run jobs, but they don't know what's happening behind the scene. They get the profiling tools, they get the values, but also being able to understand the traffic as a system level is challenging. Also, how can you find the congested links in your cluster or job or or a specific set of nodes, and how to view the network traffic for historical job. So these are the tasks. We're going to go through them. Let me stop this. So this is OSU INAM running right now on an emulator mode. So the first thing we do, this is right now, this is the emulation of OSC cluster. So if you notice, you have the topology of the logical topology of your network. This does not represent the physical connectivity, like how close they are or how far they are, but just the logical. And on top of that, we can see the link utilization by the colors here from 0 to 5, 5 to 25, and up to 75 to 100. So by exposing this to people can quickly figure out which links are underutilized or which links are heavily congested. So by this, a system admin can figure out which links are having congestion or they are causing slowdown in a network. This is a network view. There is also a view for a job and a set of nodes. So for a job, this one is also running on OSC. So I selected a running job at OSC cluster. This is a job ID, and I'm going to filter to see the communication and the link usage of this job. So as you can see, this is a 96 job size. 96 nodes are included in here. People can extend these to see what is their job topology, and that is used to understand sometimes there is jitter on your network. So as you know, there are some switches that on the route that your links are connected to each other. So having this view enables you to understand what is happening on your cluster and also job level. So you get the job topology here. Going back to the emulator, we have different set of metrics that people can use. The first two are the IB level transmitted and received data, and then we have some counters from MPI, so collected byte sense, RMA1s, point-to-point, and also symbol errors. So this is an emulation, not correct, don't panic, but people can see which links are having errors or which ones are having link down. So this is available here too. On the right side, it shows from your entire cluster. Push this. Oh, I'm only choosing this. My bad. So here it shows on your cluster with respect to all of the links, how many of them are utilized at different percentages. So we see that most of the links are only utilized between 5 to 50%, while very few of the links are utilized at 75 to 100%. Another feature that is useful is sometimes you just want to select a node and see what is running on it. So this gives you the information for the name of the node, the job ID that is running right now, LID and GUID. And to find the nodes, what we can do here, if you know the LID of your node, you can just type it in. And it'll show you this tiny one over here. Sorry, the network is really big, so it's hard to see, but this is the node that we were looking for. You all can also find the nodes by their names. So if you have specific nodes in mind and you want to find them, where are they located on your cluster, you can do that. And it shows you it's right here. Again, this is a big cluster, so you have to just zoom in a little bit and you're able to see it over here. Another set of tasks that, let me go from here, I want to demo is how can we visualize a specific job? I've shown you a job that is only for the job topology, but we want to take a dive into it and see how can we see the node level information and also the traffic information with regard to a job, a set of nodes, and a set of processes. So let's move to that. So for that, there is a tab here that shows all the live jobs right now running on your cluster. Again, this is a simulation, but you can see different values for like the data that each job has from the node counts. You can filter like to the total internode communication, and all of these are selectable through a list here, so people can choose which values they care. They can sort it or go through it. So right now, I'm just gonna choose one of these jobs and open a live job page. So in this page, I'm able to see everything with respect to like a job level or a node level. So from the CPU utilization to virtual memory usage, the breakdown is shown for users to understand what is happening on each node. Also, each of these links here, each of these nodes here are clickable to get the same view, but this time from a node and a process level, MPI process level. So that is something that helps people to follow the organization from a job to a node to a process to see how is each process contributing to the overall traffic that is being sent on the job and also on the higher level on the system. So going back, so these two show the virtual memory usage and CPU. We also have the internode communication buffer that is available for node. Similar one is also available on the process level. And if you go down, we have the process counters. These are the counters collected from MPI that shows traffic from the software. So opening these, these graphs get updated at 5. So the time goes by as we get the new data points. The gray one shows a delta. This is the difference between two data points. And the red one is the aggregate of all the data has been sent for this job. We also have the read interval shown to you, like how much, how often do we collect these data points. And we have a set of metrics that's similar to network view. They're available here from IB level, so from receive side to collective to SMP and IO. So choosing each one of these show you the data that you have and updates the graph automatically. Then we have the node level information. So this was the entire job level. So we want to take a look at single node performance for the communication pattern that we're having. So similar view is also available here. People can compare to see the traffic on the node level and also the job level. Moving forward, we also have the port counters, which is from InfiniBand counters. So you can compare your software counters at the same time with the port counters, and that is useful. So we have here like the information of the name of the node, the LID, GUID, which switch it is connected to, and the port and everything, and the read interval. So here, we also have the plot for the communication that is happening on the IB level, and you can choose different times to view this communication. So, and this chart is also like interactive, so you can play with it. And similarly, we have all the IB metrics here available to visualize. So if you just select different ones, you should be able to see the associated metric. So by having these two together, you can understand from your MPI level and also IB level what is happening and how is traffic communication from your software is getting reflected on your IB level. Let me see. Going back to our presentation. So overall, by these visualizations, you should be able to achieve all of these tasks mentioned here. You're going for the next one. Oh, I already did that. It's also like viewing the list of the running jobs and filtering jobs. I want to show a historical view of a job and also switches. And these are important specifically for system admins to see what has been happening, because a problem not always doesn't happen. At the same time, you sometimes notice, oh, 5 hours ago I had a problem. So let's move to do that. My screen is stuck here. Okay, so on the top of the page, we also have historical jobs and switches. So let's just view the historical view of this job 3423 on this page. So automatically it shows the start time of the job and 10 minutes after the end time. And it starts plotting the same graphs that we saw, but this time it's the average of the time for these CPU and memory utilization between the start time and end time. So we have the similar graphs over here. And if you want to see, for example, this CPU usage over the time, we can go over here and select it here. Oh, this was 0 already, so let me choose this one. So this shows you the virtual buffer memory usage for your entire job, and it's also available for the counters beside what I mentioned in the live jobs for each node. And also the port counters that we can get for the duration that we have selected. Okay, so let's move to the historical switch. So a lot of the times, as I mentioned, the problem in the network comes from a switch. So that this helps to select the switch that we have, shows which nodes are connected to it. So this is a root switch. As you can see, it's connected to other switches, and we can see the traffic on each ports of this switch for different metrics that I mentioned already. So this is very useful for people to understand the pattern of the traffic in a historical manner. And if people, it shows you the read interval and gathers everything. And if you notice, everything is like rendering and coming super fast. So that's one of the features we have been working hard on it to bring this to people in the community. So as the last thing, I want to move ahead and show you another feature of OSU INAM that's called notifications. So getting all of this, as you have noticed, it's me constantly pulling the data, going through the graph. So what happens if you want to get a notification of a link downer or like an event in your network? So that's why we came up with the notifications. You get an email. You can also view it here. So the way it works is you select a category that you want. So for example, like port counters, you choose a metric that you want. You want to see if any like link recovers. So if it's more than one, please send me an email to here. So, and you can set it up. Again. Oh. Oh, yeah, my bad. Okay, so you get the notification criteria is happening here. So whenever this event happens, you're going to get an email, and also it's going to be showing on the notifications area. So that's also useful for people if there is a link down here, like or something going to happen on your network. The system admin can quickly get a notification, hey, this happened. So tend to it. Or if you want to define a golden state for your network, so this is what you expect of your network. So if a certain amount of traffic is exceeding on a link, please send me an email. So this is where it's going to be useful. And as the last thing, I want to show you the database calculator. As I mentioned, so you can play around on the amount of storage you're going to need for OSU INAM to see like what should be your interval based on your network. So this gives you all the information you need in terms of like storage. With that, I want to conclude my talk. I'd like to appreciate Karen and OSC for constantly helping us for testing and verification, providing feedback. Developing this tool was not just like a simple project, it was like chicken and egg project, so they have provided us very good feedback. I appreciate you, and I'm happy to answer any questions if you have.
Any questions, guys, before we wind up? And again, as I mentioned, if you would like to play around with OSU INAM, let us know. We can try to set up a sandbox environment for you where you like play around with this. So typically we do deliver this as a like hands-on tutorial where people get a chance to like log on to these clusters and like try out these features for themselves. But again, due to lack of time, we were unable to do that. So if you're interested, please do contact us, and thank you. And yes, Moshe.
Is there any other restriction on the tool beside working only with the MUG'22?
Sorry, can you please repeat that?
Are there any restrictions on the tool beside that it works right now with MUG'22 or TensorFlow or PyTorch?
No.
So off-ed and regular any driver?
No. Yeah. Currently it works for like an InfiniBand-based system. So it has support to work with the job scheduler, like an InfiniBand fabric and an MPI library. So these are like distinct components. Okay. So for instance, currently we support PBS and Slurm. If you have a third job scheduler, then that those features which are dependent on the job scheduler will not work. That's about it. So at the very least, if it's an IB system, you will get the information about the fabric. So as you saw earlier, you'll be able to visualize the entire fabric, what communication is happening on the links, at least at that level. Now, on top of that, if you are using Slurm, then we can know what jobs were running on what node. So if you like job level information, that you can get. Now, if on top of that you have like a supporting MPI library as well, then you will be able to get MPI level information. The more supported elements you have, the more features will automatically become active.
Yeah, and if you MPI command, you could still tie it up to that, or without Slurm or anything like that?
So sorry, I was not able to hear you.
If you just use the MPI run command to launch the job,
yep,
no Slurm or anything like that, you could still tie it up to this?
Yes. Yes. Because the MPI runtime, again, INAM will automatically, let's say if Slurm is there, INAM will automatically contact Slurm. So you just need to tell INAM that, hey, there is Slurm, it is located at this location, so it is going to automatically contact it.
Slurm or PBS. So
yeah,
we
Slurm
also
or
support
PBS.
PBS. Yeah. And without MPI, you still get this, all of this.
Yes.
So what is the status of the INAM development support for GPUs?
It's under progress. So we are in an academic environment, so funding is a critical issue. So this project ran out of funding like some time back. So we are trying to do it on a best effort basis at this point in time. Theoretically, we have it working. Like we have published a paper along that direction, but to get that into production, we need some more work. The hope is that in 6 to 8 months, because of the best effort nature, we'll have it out. But yes, there is a plan. We have shown a proof of concept. We published as a paper, like Pouya was the first author in the paper. It was published 2 years ago at HiPC. So we do have that support, but we have not been able to push it out because of, let's say, practical issues.
Okay.
Any other questions, thoughts, comments, features that you would like to? Yes, Navras.
So if you're constantly monitoring the network, does that add any overhead? Especially
No.
if there are checks that you're constantly checking.
Correct. So if you remember in the presentation, we had showed an overview section, like a overhead analysis section, where we are trying to evaluate different kind of overheads from the network's perspective, from the job's perspective. Overall, no. So we have not seen much overhead, and of course it also depends on the granularity at which you want to profile the network. So if you want to profile the network at like every second or 5 seconds or so, then you really don't affect the fabric that much. If you want to do it at, like, let's say 10 microseconds, that may be a different question. Okay.
Yeah, we tested with 250 milliseconds,
Yeah.
and we saw only 5%, less than 5%. Yeah. So if you want to go below that, I don't think you don't need it, but it's going to be a little bit more.
So we can go up to sub-second granularity on a cluster about like 2,000 to 3,000 nodes without any issues. Beyond that, we haven't gone yet. So that is where all of these scalability enhancements come, and that's why we are trying to replace MySQL with a more scalable like DB backend. So we as a group always try to like go for more scalability and more performance. So that's where we are headed to, and hopefully we'll get there eventually. Yeah. Thanks. That's a good question. Anything else, guys?
We have a question from the WebEx chat.
Oh, sure.
Why is MoFed 4.9 LTS not supported?
It is supported, so maybe there is a typo. If you guys see, if you guys see a version of OFED or MoFed which is not supported, send us a note. Okay, we can create it for you. Yes.
So does OSU INAM handle streaming data or static data?
So currently it can do both. It will query it. If the data, what do you mean by static data, so to speak? If there is no change, then there is nothing to really query, so to speak. So like in general, we are more interested in streaming data because there is some change and we want to monitor the change. So we are focusing on streaming data mostly. So if the data is static, then there's something that we don't have to like.
So I'm wondering if we have streaming data, so how much latency do we have before we can visualize the data?
It is almost a real-time visualization. So like probably in less than a couple of seconds, you should be able to do it. So overall, that is the latency that we see.
Okay, thank you.
Yeah, I think we're running a bit late.
Yeah,
Harry,
sure.
So
Thank you, guys. So we are here. If you have any further questions, please let us know. Thank you. Yeah, and like we are here, so we can talk over coffee, beer, drinks, whatever. Yeah.
thank you both.